So next, what we are going to study here is related to the isolated footing. In an isolated footing, what is important is what is the soil pressure, what is the pressure uh, exerted on the soil, and what is the amount of allowable soil pressure. When we say allowable soil pressure, what do we mean by allowable soil pressure? For example, you have the footing, this is the plan of the footing, and coming to the plan of the footing, this will tell you the area, this will give you the area of the footing that's in contact with the soil. So all the forces that are being transmitted through the foundation into the soil is being transmitted through this area. So if there is a load P that is acting through the column onto the footing beneath it, this being the footing, this one beneath it, the load being P, so what if the area of this base of the footing is A, then in that case, the stresses that would be exerted would be on the top layer of the soil would be stress on soil would be P by A. That would be the stress that would be exerted onto the soil. Now, this stress, if we give resemble it by Q, then this would be the stress that is acting actually on the soil. But there is a QA, which is the stress above which the stress of the soil should not increase. So the pressure or the stress, the soil stress or the soil pressure, which is allowable, is QA. Thereby, what does this mean? Our Q should not be greater than QA, so it should be less than QA for the safety of the structure and for the safety of the foundation, such that the soil does not fail, and thereby the structure does not fail. So we limit the stress on the soil Q to less than allowable soil pressure. Now, how do we get the allowable soil pressure? Now, the allowable soil pressure is determined from the bearing capacity of the soil. So we have already discussed about this, that there is a safe bearing capacity of the soil, and that's around 100 to 400 kilopascals. So, but allowable soil pressure is taken about 2 to 6 times less than mm, this is times less than the bearing capacity of soil. So if we have the bearing capacity of say 100 kilopascals, then the allowable soil pressure would be from varying from 100 by 2, that's 50 kilopascals, to 100 by 6. So we are actually decreasing the allowable bearing capacity or the allowable soil pressure. This factor of safety that we apply in soil mechanics. uh, it's based on two things: that the soil should not fail under any applied load, and the settlements, both the overall settlement as well as the differential settlement of the soil, should be within the permissible limits. So in our design now, it's both structural engineer as well as the geotechnical consultant or the engineer, both have to be taken into board, and we had to design the structure such that the service load conditions uh, which are applicable, uh, so that our Q stays less than QA. That means the stresses exerted as per the service load conditions from the structure onto the foundation and thereby onto the soil should be less than QA, where QA is actually the the allowable soil pressure, taken into account the safety factors for the design. Now, while the design itself, uh, we could have gone for the limit state method uh, for design of the foundation. Similarly, we could go for two limit states would be there. One is the ultimate limit state, and other is the serviceability limit state. But in case of this design, uh, we usually go for partial load factors. They are applied onto the load that is coming onto the foundation, that's on the dead load, then on the live load. Similarly, on the wind load, the earthquake load, and they are uh, thereby applicable. Only the serviceability limit state is taken into account and not the ultimate limit state, because we are already applying a higher factor of safety for the soil, that is 2 to 6 times. uh, we have when we have calculated the value of QA, thereby we only go for a serviceability limit state. And what do we have in the serviceability limit state? There is dead load, live load, wind loads or earthquake loads, whatever you have, they are all considered such that the load factor is 1.0 on all these loads. So while designing the foundation and here the isolated footing, we do not multiply it by 1.5 as in for the case of the limit state of collapse, because we have already considered a higher factor of safety for while determining QA. So the serviceability limit state is considered enough, and thereby the load factor applied is just one on this basis. So um, there is one more important thing that we need to take into account, is that while we are determining the soil pressure QA, that has to be determined at a certain depth. Uh, so it's usually at a 500 depth from the natural ground level, and this QA would actually give us the gross pressure that's exerted onto the soil. Now, this includes two things. One, and there is this is the, for example, a column, then there is an isolated footing. Now, there will be, where are we? There is a natural ground, for example, here. This is the natural ground level. So we're actually determining the soil pressure at this point. So this is already within the soil. So while you are determining the gross pressure has to include the pressure of the overburden. That's the pressure of the foundation depth up till this point. From here to here, there is a already a ground level. So the overburden pressure has to be taken into account. One is the overburden pressure, and the other is the pressure that is uh, the pressure due to load. So we have two types of pressures. So one pressure is due to this load P, and that's divided by A of the footing, would P plus A. Then you have the other pressure due to the overburden from of the soil. So there will be a load exerted from the soil, which calculated from the density of the soil, and once there, then you get the overburden pressure as well. So we're actually determining the stress, that's a total stress that's exerted at this level, just below the foundation level. That's at this point here, uh, at this level. We are determining the overall pressure on the soil. So thereby, uh, we do not take the net pressure, we take the gross pressure while calculating the allowable soil pressure, that's QA. And hence, what we can say that the total load that has to be considered in calculating the maximum soil pressure QA has to be less than Q has to be less than QA. So it includes the weight of the footing and that of the backfill as well. So the footing weight should also be calculated while determining QA. Thereby, how do we calculate these? For example, we have not yet designed the foundation. So how do we go ahead and calculate initially because this has to be the first step while determining QA. How do we know how much is the foundation and how much is the weight of the foundation? So by convention, we usually take around 10 to 15% of the weight of the footing. Uh, so we are actually take the weight of the it's the 10 to 15% weight of footing. So that converts into load of what? Of the actual load that's coming through the column. So if the column, the load that's coming P that's coming through the column onto the footing is around say 2000 kilonewton. So you are taking 10%, 0.1 of 2000, for example, up till 0.15, somewhere in this range, to know the weight or the load coming of the footing. So there is an addition of uh, 2000 kilonewton plus zero point 0.1 of 2000. So the load, the weight of the footing that we are considering is actually increasing. So now when we are know the soil pressure that's exerted onto the soil, and we know the allowable soil pressure, by using this methodology wherein we are taking the ultimate limits, not the ultimate limit state but the serviceability limit state. So we actually then need to know the how these pressures are distributed of soil pressure. Now this is very important, how the soil pressure is actually distributed in the soil. Now let me go through this. For example, you have uh, so this is the footing, and there is a load coming over this footing from a column. Now usually what would happen, i would uh, I would like that you all uh, check what would happen at your own places. For example, the load is coming here, where would this load go? There is a soil. This is within the soil already. So there is a soil envelope here, and for example, this is the soil envelope here. All this is soil. Now, just try to guess what would happen to this load. Where would it go? It would be distributed like this. Would it be somewhat like this, right through going into the soil? Then what would be the reaction of the soil? Somewhat like this. This is the reaction of the soil. So the resistance offered by the soil to the footing. So thereby, is this really feasible? The column is quite a small area as compared to the footing. Does it distribute very evenly and go to all parts here? What do you guess? Because this footing is actually it's embedded into the soil. So we would normally assume that the footing being embedded in the soil, to the footing being a rigid structural element, it does not bend. It does so thereby the footing is distributing the load evenly onto the soil. Due to its property of not bending, it's somewhat like you have a steel plate, and although you apply the load, but the steel plate or the copper plate is quite thick, it's not bending. So even if it's resting on sand, that steel plate, there would be a total reaction offered by the sand itself onto the steel plate. So it would leave a mark on the sand, the steel plate, but the sand would not go down. So thereby the sand has offered some reaction to the load that you had applied on the steel plate. So now if you move that steel plate quite further down into the ground and then apply the load, now there is a much better resistance being offered by the soil underneath it or the sand in which it's placed. So a rigid construction of this footing is the first uh, thing that you require while you are designing this column, this footing. Thereby, what we are assuming that the distribution of the pressure from the soil is even, it's uniform throughout the footing. Uh, this is the first approximation, not an assumption. This is an approximation that we are getting, that the distribution of the pressure reactions from the soil to the footing are uniform, and they do not vary. They do not change. For example, it would not be somewhat like this, that there is a large amount of a reaction at one end and or at the center and quite less at the ends, like this. It's a triangular reaction offered by the soil. No, we assume that it is uniform. The reaction is uniform throughout. Now if the load that is being applied here is P load, so thereby if there is a certain more load coming from the overburden pressure, which is for example, it's let me write as, just a minute. For example, there is delta P. Delta P is the load that's coming from the overburden. Thereby, the total Q would be P plus delta P, and this would be divided by the area of the footing, which is A. So this will be the load that's the stresses that are being exerted onto the soil from the footing. Now, there is one more important thing when you are taking this into account, that the weight of the footing and the backfill that you are taking. Again, you must realize that this is up till the point, the lower point of the footing. So all this load uh, of this much portion, let me show this again, of this portion plus this portion, this and this portion needs to be taken into account, this and this and this needs to be taken into account, and that makes up delta P. So that you usually we take it as 10 to 15% of P. So thereby, now having known the Q value and that being distributed evenly, so you would say that Q is this. If it's a total reaction offered by the soil and the soil is not yielding, it's not failing, then Q is the reaction. So how would this be? This would be, its units would be kilonewton per meter square. So it would be over an area of 1 unit meter square. For example, it's kilonewton per meter square. So this is over a unit area. For example, now this is the plan of the footing that you have. So there is certain 1 meter square of the area of this footing, 1 meter by 1 meter. This is 1 meter by 1 meter, over which there is a uniform distribution of pressure exerted from the soil onto the footing. And how much is that? That's Q. So this is actually an area load now being exerted as a reaction to the footing from beneath. So the red arrows here, they are exerting the pressure onto the footing from the soil. Now, you would be confused what is happening. While we are designing the slabs, the load was coming directly onto the slab from the top. Now, here you would say that there is a footing and the load is coming from beneath onto the soil. You would say this is confusing. There is the column above it. Load to wahan se aa raha hai. The methodology of the design should be such that the load is coming from the top, that's from the column onto the footing. But why are we applying the load in the reverse direction? In this case, let me try to check what is the behavior of this footing. What would happen to this footing once you have a column above it? There's a column here. There's a footing here underneath it. You would normally say that under the load, weight of the load, the bending of this footing would be somewhat like this. It would bend under the loads in this fashion. Would it be like this, or would it be like this? This is it the first case or the second case? The first case is the most likely case, not the second case. Why so? Why do I say this? Because the load is coming from directly from the column here and it's being transferred onto the footing. So this portion just below the column, there would be more tensile forces acting on the lower side here, and it would be opposite towards when we go towards the edge here. The the tension side would move towards the top. Is it so? Do you think this is how it behaves? If this is the case, what is the role of the soil beneath it? There is a soil here that's holding on this footing. It's exerting reactions onto this footing. It's not allowing it to bend. So it's offering the reaction to this footing. Now, this is a typical case of an inverted. If you take this inverted, if I reverse this like this, let me just reverse it, the system like this. Now, what do you realize? There is a UDL load acting onto this footing, and there is a support at the center of this. Why is there a reaction? First, you need to understand why are we taking the reaction and not the load from the column onto this? Why are we taking the reaction from the soil? Look, soil is an ultimate mass. It has got no boundaries. So as compared to a building, it's an ultimate mass. It's an infinite thing as compared to the structure. So it's natural to expect that the reaction will be from the soil onto the footing, and that reaction will be greater than what is the load that's being acted on the soil, unless and until the soil does not fail, the top layer of the soil does not fail, and the structure then does not settle and collapse within the soil, or bear within the soil. So until and unless the failure is the design is okay, the failure and the settlement is not happening. So two things are not happening. That is, the collapse is not happening on the soil, and the soil is not giving in. Then this is a natural reaction that there is a total. The reaction offered by the soil is absolute and uniform onto this. So it can be treated as there is a UDL load acting onto this system, and there is a support in the center of this, and that support is actually taking the UDL load. So under this system, now what do you expect? This is a cantilever on this side, right? And thereby the bending would be like this, and there is a cantilever on this side, the bending would be like this. Now again, if I reverse this, now what do I get? At the center there is sagging, and towards the ends there is hogging happening here. So our design should be based on these principles, that towards the end of the footing the hogging predominates, and at the center beneath the support the sagging predominates. So our design philosophy should be based on this behavior of the footing. Now this is a similar case like a slab design, but in case of slabs you have actually the supports towards the end, and then the hogging is happening. Here there is no support towards the end, but the support is at the center. If I reverse this system, thereby what we are doing in the design, uh, so what have we got from the uh, distribution of the base shear, the base pressure, is that the area that is now required, what is the area now required for design of footing? It has to be P plus delta P by QA. Q was the stresses exerted from the system, and QA is the This is the allowable soil pressure based on what is the maximum limit up till which you can go. So the area of the system that's required has to be at least this is area at least required, at least the minimum required has to be this much for the system. So this footing now has to be designed for an area of at least for an area of P plus delta P by QA. Now, this was a case when the soil was being loaded concentrically. What would happen if the soil was being loaded eccentrically like this? For example, you have a column, in this case is at one end, it's not concentric. So this is being loaded at a distance of E. So there is an eccentric application of load P. Now, why would anybody go for an eccentric footing while designing this? Probably there is a offset on one side, and there is another building or something else, so you cannot, and there's a property issue, and so you cannot go towards that side for footing construction. So you need to design an eccentric footing then in that case, where one side of the footing is quite large as compared to the other side of the footing. So thereby an eccentricity arises in the design of the footing. So in this case, what would usually happen is that the resultant of the forces that are acting on the soil are now eccentric. So the resultant thrust exerted would be shifting towards one side,